Okay, Secretary Acosta, Dr. Palma, distinguished guests from BIFAR, from FICAR, from LLDA, distinguished guests from the media, ladies and gentlemen, good morning. Okay, so the motivation behind this problem has been clearly laid out by Secretary Acosta's talk earlier. What I will be dealing with is more specific solution to the problem of night fish infestation in the Laguna Lake. We have me and a group in Ateneo has actually submitted a proposal for carrying out this solution. So what I will be talking about is mathematics, acoustics, and anatomy towards engineering a bladder blaster. I'm Juanico, Assistant Professor at the Department of Mathematics at the de Manila University. Okay, so probably this is a very familiar trick that you might have encountered before. So the wine glass, if you put your finger at the rim and then trace out the rim of the wine glass, you'll actually realize that the wine glass has a specific tube. Who among you have done this before? So maybe you could try it out with your wine glass after your lunch. What happens is, when you put your finger in the rim and you hear that tune is actually referred to as the natural or resonant frequency of the wine glass. What that means is it is at the specific frequency that the glass vibrates or shakes. Now once you have gotten the correct value of that frequency, and you have a speaker near the wine glass, and then you project that same frequency onto the wine glass and turn the volume a bit louder, we will actually see that the wine glass is shattered. I have a simple video to demonstrate, video piece on shattered wine glass, how the process actually works. Okay, so the setup consists of a sound coming from a speaker of a certain pitch. This is the speaker, this is the wine glass, and when the sound is made louder, that particular frequency, I suppose, no. So if this pitch is loud enough, the glass will eventually shatter. You saw earlier that the glass was actually shaking. There, it was actually shaking. And that shaking is caused by the stimulation coming from the speaker. The speaker is not really touching the glass, but the sound waves coming from the speaker makes the shaking bigger and bigger in amplitude. And eventually, the material, the glass, breaks because it cannot anymore take the capacity of the shaking. Right, my slide again, please. Okay, which brings me to a very special concept that is widely known in physics. It is known as acoustic resonance. So what is acoustic resonance? It is the tendency of an object, usually hollow, just like the white glass earlier, capable of vibration, to absorb more energy transferred to it in wave form if the wave's oscillation matches the natural frequency or resonance frequency of vibration than other frequencies. And if we see it in the graph, if you consider the height of the graph to be how large the shaking is, and the horizontal line here to be the different values of the frequencies or the different pitch of the sound emitted by the speaker, you will see that a particular pitch, the height of this peak is very large. That pitch is the natural frequency. Only at that pitch will the glass get shattered. At other pitches, no matter how loud play that sound, the glass will not shatter. If it's too low, or if it's too high, the glass will not shatter. And there is a very wide application of resonance in broadcasting. In fact, everywhere around us, there's an invisible set of electromagnetic radiation coming from the broadcast stations of the different radio stations or different TV stations. Now, how is it that if you have a tuner and then you turn the dial to a particular frequency, say 101.9, you get only that station and not the other stations that are present in the air? The reason is because you're actually tuning your radio using a particular circuit that has also a natural tendency to vibrate. And if you tune the vibration in such a way that it matches with the frequency of the broadcasting station, then you will actually hear that station and that station alone. Okay? Now, how can we make use of the idea of acoustic resonance in relation to the knifefish problem? So, if we look at the interior anatomy of the knifefish, we will actually see that it contains a hollow object. And that hollow object is known as the swim bladder. How is this useful to the fish? The swim bladder is actually used to control or aid in controlling buoyancy. So this bladder here takes in air and can expand or contract according to the amount of air that is inside that bladder. Okay, so only fish of class Actinopterygii has such an interior organ as the bladder. And knifefish, Chitala ornata, is luckily one of those types of fishes that has a swim bladder. The swim bladder is an evolutionary homologue to the lungs, meaning to say it is actually also used to serve as a resonating chamber. Now, what is this? It's just like the wine glass earlier. It's a hollow object, but it can vibrate. And this swim bladder is not only used for controlling the buoyancy of the fish, it can also be used to produce and receive sound, meaning to say that the swim bladder is also part of the auditory system of the fish. It's like part of its ear. Now, what happens when the swim bladder is disrupted, such as by having a puncture or a rupture as part of it? In my next video, I will demonstrate what happens to the fish if its swim bladder is disrupted. Okay, so in my example here in the video, I actually show not knifefish but rather goldfish. So it is one of the is a reminder. So you can see this fish is normal, this is not. And what happens is that this fish has a disrupted bladder and it cannot anymore control its buoyancy, so it floats upside down. Okay? So the reason why the fish needs a way to control buoyancy is that it will be able to save some energy in swimming. So when it wants to stay at a particular depth of the water, it just uses the swim bladder to maintain at that particular depth without any more swimming. Okay, so to my slide again. This is an actual radiograph, an X-ray of a knifefish taken from this paper in this journal way back in 1982, and it clearly shows a hollow interior organ. This corresponds to the swim bladder. Okay. Now, here's my proposed method. So, based on the fact that we already know that the knifefish has a swim bladder, and that the swim bladder is just like a wine glass, it is sensitive to sound, then the proposed method is actually about blasting this bladder. Either we puncture a hole into that bladder or we rupture it. And that's the only way that we can disrupt as well the life cycle of the fish. The knifefish in particular. Alright, this happens usually when the knifefish is exposed to pressure variation. And incidentally, sound is actually a pressure wave. So meaning to say, sound travels in water by means of a decrease, an alternating decrease and increase in pressure. So meaning to say, it is going to be effective in stimulating the vibration of this interior organ inside the knifefish. And there are many evidences in literature which have shown the effectiveness of rupturing the swim bladder by means of sound. Okay, so we have articles from different scientific journals, and in fact, even the U.S. Army Engineering Corps also has found that sound of a particular fish can disrupt the swim bladder of fishes. Alright. But there are some practical considerations. First of all, how do we know the natural frequency of the vibration of the swim bladder? Because we cannot tune in the way we did with the wine glass, like with our finger, right, manually. So it's not that easy. Furthermore, the bladder is elastic, meaning to say it can change its capacity to certain vibrations. Furthermore, another complication is the fact that fishes are actually mobile in reality. I mean, you can't put a knifefish in one place and then expose it to the sound needed to disrupt its bladder. And furthermore, the property of the bladder in vivo is different from the properties of the bladder when it is dead. So meaning to say, if you take a knifefish, kill it, dissect it, and then examine the bladder will not be the same as when it was alive. And this will have effects on the properties of this bladder as well in relation to sound stimulation. So if we cannot physically examine the bladder while the knifefish is alive, then I propose a method which is rather indirect but may be effective in figuring out what the value of this natural frequency is. So I have here a mathematical model. Okay, this is, by the way, this is the only equation that I will show in my presentation. So I just want to emphasize this variable here. The letter W stands for the value of the frequency. So whether it's 101 kilohertz, 200 kilohertz, or whatever number you can think of, this is the W. What is represented by the W. Now it is dependent on another number, which is represented here by the symbol E. Now what is this E? This E has something to do with the shape of the bladder of the fish. The ideal shape that, from which this mathematical equation is based is a spherical shape, a spherical bubble. So we think of the bladder something like a bubble, but its shape is a sphere. But that is not ideal, because as we have seen in the radiograph earlier, the bladder is actually elongated. And so we have to make adjustments in this equation. And that's the reason for the appearance of the E in this equation. This E here is the elongatedness of a prolate spheroid. Now, prolate spheroid is like the shape of a rugby football. So it's not spherical, but it's rather a stretched sphere. So accounting for that shape, then we will be able to calculate somehow the value frequency of vibration of this swim bladder. Alright, now what this equation tells us is that the more elongated the bladder, the lower the resonant frequency. Let me translate that in more layman's terms. The more stretched the bladder of the fish, the lower the pitch of the sound that you must use to stimulate its vibration. Alright? Because frequency of sound has something to do with its pitch. Okay. So, the question now is, if we have sound as a way to target knifefish in Laguna Lake, is this strategy actually species specific? Meaning to say, will it only be able to target knifefish and not the other fishes that are in Laguna Lake, such as the very important bangus? Okay, now, based on the equation that I showed in the previous slide, the thing is, the shape of the bangus, in comparison with the shape of the knifefish, is dramatically different. Why? The knifefish is more elongated. compared to bangus and perhaps tilapia and other endemic species in Laguna Lake. So the knife fish is in fact very special if you look at it in terms of its shape. Alright? And because it is elongated in shape, we also expect that the swim bladder inside this fish is more elongated compared to the other fishes in Laguna Lake. What does that mean? There is only a particular frequency wherein the knife fish is affected and not the other fishes. This is the kind of frequency that I will be targeting, okay, by means of the mathematical equation I've shown earlier, in order that we can use that frequency to only disrupt the swim bladder of knife fish and not the other fishes. And the technology to implement this proposed method is actually available. In fact, in the talk after mine, there is a demonstration which also uses sound. And there is a technology to generate sound underwater. And this has been used commonly in sonar. So you probably have heard of sonar. And this is for detecting the location of fishes. Now, we can actually tune the pitch that the sonar emits so that it will not carry out detection, but rather disruption. So it's attacking the fish using the sonar. Alright? And the thing is, underwater, the sound can propagate over longer distances, unlike in air. In fact, if the intensity of the sound from the source, 1 meter from the source is 200 decibels, 1,000 meters or 1 kilometer from the source, it didn't really decrease that much. Okay? Unlike in air. So, a setup like this, which consists of a wave generator, oscilloscope, power source, and a speaker, can easily be made in laboratories. Okay, just like probably here in TIP. Okay, so essentially my method is theoretical and it's about zeroing in on that value of the pitch that we must use in order to target knife fish and knife fish alone. Okay, once the device is made, we can do some preliminary test using aquarium, where the knife fish is probably placed along with another species, and then we can test if the frequency really only targets the knife fish and not other species of fish. So I would like to thank Dr. Salmo and Mr. Labatos from the Environmental Science Department of Ateneo de Manila, Dr. Cabral from the Math Department of the Ateneo de Manila, who I wrote a proposal about for solving the knife fish problem, as well as Dr. Diocaris for guesting me one time last month in his radio program with the scientist, also talking about this proposal. Thank you very much for your attention.